So, welcome to our next revision lesson on waves. I still can't get into my documents, but I discovered that I had previously opened this PowerPoint on Keynote, which means I can't access it again because I can go through Keynote as opposed to going through my documents. Anyway, I'm sure you don't care, but this is Waves Part 2. Oh, that's meant to be Part 2, there you go. And today we're going to look at phase difference and a bit of interference, superposition, etc. So, let's start off with phase difference. A wave can be represented by either a displacement distance graph or a displacement time graph. Why is everything gone a bit funny here? Hang on. Shuffle these down. There you go. These graphs show how the displacement of the wave varies away from the equilibrium position. So I've got two graphs here. On the left-hand side, a displacement distance graph. Now, this is like you are physically looking at a whole wave. And you can measure wavelength. In fact, let me just write on this. Where are we? Make it smaller. There you go. You can measure wavelength and amplitude. They are the two things that you can measure from this. On the right-hand side, you'll see a displacement time graph. This is where you look at one particle. Okay, that's like a snapshot, they describe it as, where you're actually just looking at the wave. But on the right-hand side, one particle and how it moves over time. You cannot measure wavelength from this. Instead, you can measure time period, frequency, and amplitude. As in frequency, you can do 1 divided by time period. So just a quick note on that. The most common thing that people make mistake on is that, as I say, they try and measure the wrong thing from the wrong one. So just have a look at your axes. Hopefully it's not too hard there. So, on the two different waves, on a displacement distance graph, you can have different particles. And so on that one on the left, you can see there's a red, a green, and a blue. They can represent particles at different points in the wave. And sometimes we might want to refer to how they are moving in comparison to each other. And we do that by talking about phase difference. So if you have two waves travelling at the same time, or two particles on the same wave, you can calculate the phase difference between the two, and it's measured in degrees or radians. So I'm sure you remember this, but just a quick note about degrees and radians. Formatting here's gone funny. Hang on. Oh no, what have I done? Oh, I'm just trying to move this down. Oh no, okay, right, sorry, I'm going to have to put up with funny formatting. The circumference of a circle is, you know what, doesn't matter about that, but the key bit is 360 degrees is 2 pi radians. To convert, but 180 degrees is pi radians. To convert from degrees into radians, multiply by pi over 180. To convert from radians into degrees, multiply by 180 divided by pi. So I tend to just remember that 360 degrees is 2 pi radians and work from there. If I'm honest, that's all I really remember. You are not expected to know the definition of a radian in order to use it in physics. It's just that you are expected to be able to use them. That's it. So yeah, either 360 degrees, which is a full cycle of a wave, so one whole wavelength effectively apart, or 2 pi radians, and then you can work from there. So these waves are in phase with each other, or a full wavelength out of phase. They may have a phase difference of 0 degrees or 360 degrees, 2 pi rad. Now on that note, they might have a phase difference of 720 degrees if they're two wavelengths out, which would be 4 pi rad, etc. But if I'm being honest, they don't tend to do that. They tend to stick to the lower end. So the fact is they are in phase. However, these waves are in antiphase with each other. They are half a wavelength out of phase. We say they have a phase difference of 180 degrees or pi radians. It says, turn to page 196 of your textbook and copy fig 5. Well, I shall do that for you. Let's just give me 1 second. Page 196. So you don't even need to go to a textbook. I'm trying to do it for you. Aha! So, I hope you can actually read what that says. Phi here is a phase difference. X is, what's X? Distance between the points. Lambda is obviously wavelength. And then 360 degrees or 2 pi. So phase difference is effectively the proportion of a wavelength that the 2 points on the wave are different times 360 degrees or times 2 pi. So if you've got a whole wavelength, obviously you end up with wavelength over wavelength times 360, hence why you get a phase difference of 360. Or you end up with, if you're half a wavelength out, half times 360. So you can see how that works out. Right, so that was phase difference. Quite enough of that. Now let's go on to superposition of waves. When two waves meet, they create a single wave. The principle of superposition of waves states that when two waves meet at a point, the resultant displacement at that point is equal to the sum of the displacements of the individual waves. And that one is a memorize it. They like to ask what the principle of superposition of waves is. So please memorize it. On the right-hand side, you will see a diagram or a series of diagrams. Two waves coming at each other. And they're getting closer, they're getting closer, they're getting closer. Oh, here they are superposed on top of each other. Then they come out the other side and they carry on travelling on their way. And you can see that middle one where they are superposed on top of each other, the displacement is twice as high. Because as established, the resultant displacement will be the two displacements added together. Now, you can either have constructive superposition or destructive, and we'll look at those now. So interference, when two waves, should I make this bigger? It's a little small. I feel like it would be nicer if it's bigger. Come on. Oh God. Oh God. There you go, slightly better. I still don't like it. I know I'm being fussy, I'm sorry. Let's just give a bit of a... There you go, much better. Okay, when two waves continuously pass through each other, they superimpose and produce a resultant wave. I'm sorry, I know I'm being fussy. I'm just getting rid of superimpose and putting superpose. Superpose, like a really great model. This is called interference. If the two waves are in phase, the resultant wave has an increased displacement. This is constructive interference. If the two waves are in antiphase, the resultant wave has a decreased displacement. This is destructive interference. So on the right-hand side, as normal, here are some diagrams. The top diagram, you can see two waves which are going to be combined on top of each other. They are both in phase with each other, even though their amplitudes are different. And so when plotted on the same axes, you can see the resultant wave has a higher amplitude because you add them together. On the bottom diagram, you can see the same two waves, but this time they're in antiphase with each other. And so when plotted on the same set of axes, you can see they are at different points. And so to work out the resultant wave, you take their amplitudes away from each other. Intensity is proportional to amplitude squared, and that is something they love to bring up in questions. Intensity is proportional to amplitude squared. In constructive interference, intensity is increased, so sounds appear louder and lights appear brighter. In destructive interference, the intensity is decreased, so sounds appear quieter and lights appear dimmer. If the resultant amplitude is 0, the intensity also falls to 0. That makes sense. Right, coherence. And again, they love to ask you about coherence, so this bit is memorizing. Where waves have the same frequency and a constant phase difference. Now that doesn't mean they are in phase, it means that the phase difference stays the same. So they might always be in antiphase, but that's okay, they are still coherent. You can't create interference patterns using the light from a filament bulb as they emit a range of frequencies with a constantly changing phase difference. So, where the wave, maximum and minima, where the waves constructively interfere, a maxima is created. Where the waves destructively interfere, a minima is created. So on the right-hand side, you've got a diagram. You've got two loudspeakers creating waves. Now, the peak of the wave is shown by the line. In between the line, this blank bit will be a trough of a wave. So imagine you're looking at the sea. The peak of the wave is what you see. So you've got peak, 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 etc. going out. Now the green dots, you can see peak meets peak. there. And so you're getting constructive interference. So peak, peak, peak. On the middle lines here, oh no, sorry, what did I just do? Don't want that bit. Okay, on this section here, you've got the peak of a wave meeting the trough of a wave. So you've got the peaks coming from the loudspeaker on the left and the trough being provided by the loudspeaker on the right. So everywhere on that blue line will be destructive interference. It'll be quite quiet. The next line, you can see where you've got peaks and peaks meeting. Fabulous. You've got that nice, you've got that nice loud sound. You've got constructive interference and so on and so forth. So what you need to be thinking is peak meeting peak or trough meeting trough? That also works. Or is it peak meeting trough and then they cancel out and you get that destructive interference? So something that's very similar to a phase difference and people quite often get confused is path difference. The difference in the distances travelled by the waves from their source is called the path difference. If the path difference is 0 or a whole number of wavelengths, then the waves will arrive in phase and there will be constructive interference / a maxima. If the path difference is an odd number of half wavelengths, for example, 3 pi over 2, that's an odd number of half wavelengths, then the waves will arrive in antiphase and there will be destructive interference / a minima. So here, no, there's far too much information, hang on, let's go to this. Okay, so, less information. Okay, let's focus on this. You have diffraction going on here. You've got waves coming here and the tops of the lines there represent the crests of the wave. You can see they're going through two slits, which is S1 and S2. And then on the right-hand side, you can see that they are diffracting outwards. And because of that, you're getting constructive and destructive interference. Now, what I'm going to do on here already is labelled the central maximum, the different minimums, etc. I'm going to put 2 columns on here, one for path difference and one for phase difference. Now remember, path difference I'm going to refer to in terms of wavelength, but you could also do it in terms of meters if I knew the actual wavelength, and phase difference will be in degrees or pi radians. So, central maximum, let's start with that. There is no path difference. They both travel the same distance, and there is no phase difference. They're completely in phase. The first minimum, even, is going to be pi over 2 for their path difference, and the same on this side. And they are going to be, I'm going to do it in pi just to make life easier. It's less writing for me, if I'm being perfectly honest. They're going to be pi out of phase with each other. Then, the next maximum, they will be a whole wavelength out, and they will be 2 pi, gosh, sorry, it's quite squashed, isn't it? 2 pi of their phase difference. Next one, second minimum, they will be 3 pi over 2, 3 lambda over 2 as their path difference, and they will be 3 pi their phase difference. And likewise down here, 3 lambda over 2 and 3 pi. Hopefully you're getting this now. Second maximum, they will be 2 wavelengths out, and they will be 4 pi as their phase difference. Now that's really handy if you can work that out, because questions may give you the path difference, say it's the second maximum, and then get you to work out the wavelength or work out the phase difference and things like that. So I'm hoping that's quite handy. Right, we're nearly at the end. No, we're not. That's a complete lie. Let's look at Young's double slit experiment. Mouthful of tea there. So, why is this important? Newton, we know, great physicist, etc., thought that light was a particle. And they treated light as a particle. And then in 1801, Thomas Young, who was a very, very clever man, proved that light was a wave. I know now we talk about light being both a wave and a particle, but, you know, we're talking classical physics here, not quantum. So, yeah, massive revolutionary here. So what they had was a compact light source, lovely, with a filament. They then had a double slit. Now, just a quick note that it's much easier to do this with a laser, because a laser produces monochromatic light. which means that you get a really clear interference pattern. They didn't have lasers in 1801, so, they just did it with a normal light bulb. So then they've got double slit, lovely, and then they've got a screen, basically. So what did they see? They saw fringes, which is these very, very bright lines, but also these very dark lines. And we now know that they're caused by constructive and destructive interference, but Newton's particle theory of light couldn't explain that. In Newton's particle theory, either a particle went through and it was there, or it didn't. Particles aren't meant to diffract. Again, I know in quantum, but we're ignoring it for the time being. Particles should not diffract. They either go through or they don't. They don't spread out. So there is an equation. Wavelength is ax over d, a being the distance between the slits, x being the distance between the fringes, d being the distance between the screen and the splits. Now, everything here is measured in meters. And that's it. We're going to pause there. The final video that I'm going to do later on is all about stationary waves, but again, I feel like it's best to split things up. So I hope you've paused the video. I hope that was enough information, and I shall see you later. Goodbye.